All right, here we go. So last week I uploaded the videos, but I accidentally forgot to put one of them in there. I did that this morning. It's there. Part 3 was missing, so it's there now. Right there, please. Yes. All right. Did you have a good weekend? Yeah. I don't know, this time change, actually, I feel more tired than I normally do. Normally, it's supposed to help you, right? You get an extra hour. It feels worse today than it has on any other Monday.
Or overnight, so I came in at 1.
Yeah.
And it was 2 o'clock.
Yeah. You're young, though. You're young. All right, a lot to do today. We're going to start our new coordinate systems, right? Do we need a recap? 12.5, this is 12.6. 12.5, we're doing triple integrals. We saw that when you do triple integrals, you could do it, the most basic shape was a box. Then we went on to these others where we were looking at the shadows on the ground. They were either type 1 or type 2. And we could even have things projected onto different planes. If you have your take home, please turn it in up here. If not, remember you only have to turn in what? 7 of the 8? No, I'm kidding. 6. 6 of them, right? You only have to turn in 6. So if you're at a point where you're happy with your grades, with the 6, how many have we had? 5. This is 5, so the one that you have now, you can stop at that point. All right, so what we're going to do today is we're going to talk about triple integrals in 2 different coordinate systems, cylindrical and spherical. We're going to go in that order, and I think we'll probably finish it up and get into the last section of this chapter. And that'll set us up for starting the next chapter, last chapter of the book, next class, all right? So triple integrals in cylindrical coordinates. So remember with a triple integral that, do it off camera here. When you have a triple integral, this right here, this E is some solid, right? That lives in 3-dimensional space. The function's in some other dimension, right? So we're really just trying to get some sort of way to define that solid. Cartesian coordinate system is great for a lot of them, but there's others that it's not so good for. So let's go back and remember when we talked about polar coordinates, right? There was a way to convert from Cartesian to polar. This is when we were doing double integrals. And pretty much it was this picture. Ignore the Z there for a second. Just ignore this. This is the picture in 2-dimensional space. We had r, right, with some radius, and we had theta. Instead of giving an x and a y coordinate, just give me an r and a theta, and I can move around 2-dimensional space. Well, we want that same sort of idea, right, but now we want this in 3-dimensional space instead of 2-dimensional space. So we want to get to the x and the y, we want to use the polar conversion. And then the z coordinate is just going to be z from Cartesian. So cylindrical coordinate system, the cylindrical coordinate system is basically your x and y are converted from Cartesian to polar, but your z stays Cartesian. Nothing happens to z. It's just z is z. So you'll hear me when we're doing triples. Sometimes you'll hear me say, okay, now we got to go to polar. Really what I mean is we're cylindrical, but cylindrical is just polar in 3-dimensional space. Okay? Now, the reason they call this cylindrical coordinate system is because if you look at the shape of a point here, if we were to take the radius, if we were to change r, what that does is, oh, that's not what I meant to do. If we were to change theta, it would spin around, right? And if we change z, we move up and down. If we change the radius, it gets bigger and smaller, right? But when you look at that shape, it looks like a can, right? Like a cylinder. And so that's why we call this cylindrical coordinates. Now, just like we've done in the previous triple integrals, what we want to do is look at these different type regions, right? These different type regions. So what we're going to see here is this generic region here. So notice that in this generic region, this is the ground, this is X, this is Y. So it's kind of a weird perspective I have here. Do I want to move this? I don't think I want to move it, do I? Oh, shit. Well, that didn't help. It's making me dizzy. Yeah, that's not so bad, I guess. So this is the X, this is the Y. So we have our thetas between two constants, right? Our radius is between, it looks like in this picture, between two constants, right? And then we have our Z is between two functions of X and Y. So we have some bottom surface and top surface. So really, the only difference between Cartesian triple integrals and cylindrical triple integrals is the shadow on the ground is no longer type 1 or type 2. This is a polar region on the ground. That's the difference. So here is the formula. All right. If our theta is between two constants, our radius is between two functions of theta, and our Z is between two surfaces. Notice that this Z here, it says U1, that's the first surface. This is really X and Y, but see, I've converted over to polar. And then this is the second surface, X and Y, but I've converted to polar. Then this is our triple integral, and I've highlighted here in blue. I mean, in blue? Really? Yeah. In yellow. What the fuck? Okay. That means I'm really tired. Okay, I've highlighted in yellow, right? R. That comes from when we go to polar, right? You have to have that R in there. Same with cylindrical, it's going to be there. All right, let's just do an example. Best way to get used to this, just do one. Find the triple integral over the solid E, right, of the function we're integrating is very simple, x. With respect to what? With respect to volume, right? With respect to volume. So let's look at our region. E, the thing we're integrating over, the region we're integrating on is going to be z equals 0, right, which is the floor. Z equals x plus y plus 5, that's a what? Plane. A cylinder of radius 2 that opens, the cylinder goes which axis? Out the z-axis because the z is missing. And then another cylinder of radius 3. Yeah, same axis. So you've got the ground, right? You've got the ground. You've got some plane. And then you got two cylinders punching through those, right? And we're trying, the solid we're integrating over, let's see, the solid we're integrating over is that solid bounded by all of those. Should we try and draw it? Or just have the computer? You want to just have the computer? Can you at least, let me sketch it. There's the ground. There's a plane at an angle. There's a cylinder. Another cylinder. Do you see the region bounded by all of those? So I think the easiest way to look at it is between the two cylinders, it looks like, I don't know, what shape is that? Like all the way. A tube with a very thick wall. What looks like that? PVC, but thick wall, right? So you have like a pipe, right? You have a pipe, then you have a plane cutting it on the bottom and a plane cutting at an angle. Like a pool noodle? Yeah, pool noodle. Yeah, there you go, pool noodle. It has a hole in it. Most of them do. Okay, so there's the more accurate picture, right? And we are trying to find the solid. So let me pull all the surfaces back. There we go. That's solid. Okay, this is the region, the solid we are integrating over, right? It's the solid we're integrating. You want to turn that in? I got your text, yeah? Okay, thank you. So that's the region we're integrating over. So let's think about this region for a second. What is the shadow of that region on the ground? What's the shadow of that onto the ground? It's like a circle, and inside of it is another circle, right? And that shadow on the ground is perfect for polar, isn't it? This is a great polar region. So we want to do this in polar, which really means cylindrical because it's a triple integral. So that's why we're going to switch this over, right? So let's see from that. Yeah, let's see if we can actually talk about if we're going to go to polar. See, I said it already. If we're going to go to cylindrical, which is polar, okay, then we're going to need some restrictions on theta, on r, and on z. All right, so for this picture on the ground, what's your theta between? 0 to 2 pi, all the way around. Okay, what's your radius between? Well, this is where the cylinders come into play, right? It was 2 and 3, right? 2 and 3. So 2 to 3. And then z stuck between, so the plane on the bottom, 0, and then that plane on the top, which I scrolled away from already, x plus y plus 5. Right? Pardon?
Are we going to change it?
Yeah, so, but we converted, right, to polar or cylindrical. So this this should actually be z greater or equal to that, 0, and then this should be r cosine theta, r sine theta, plus 5. Because we are switching, right? We're switching it. We're no longer our x and y are now converted to r and theta, so we have to make the polar conversion. I think that's it. We can set up the integral now. Let me go ahead and come in here, right there. Okay, so we've got the triple integral over e of x dv should be equal to triple integral. All right, I've got 0 to 2 pi, 2 to 3, 2 to 3, and then 0 to, yeah, it's going to be an ugly upper limit of integration, isn't it? Look at that. Your upper limit of integration is this entire thing. And then what are we integrating? X. Okay, so x, what is x if we've converted to cylindrical / polar? R cosine theta. So we're integrating r cosine theta times r. So don't forget that blue r that I had up there a little while ago, right? You have to have the r in there because we converted. And then you need your order of integration correctly here. So d z. So z doesn't change in cylindrical. Z is z. And then d r, and then d theta. There we go. And then we just have to evaluate that. So you have to do this first, right? I'm not going to do the work. I have the computer do it for us. But just to remind you, this is really this, right? Okay, you have to integrate that with respect to z first. So this is all just a constant. So the antiderivative of that with respect to z is just this times z. Then you plug in, imagine plugging that in for z. Like imagine next to this is all that. Then you have to distribute through, and that looks like a whole like Cal 2 bunch of crap, right? You're going to have cosines and sine squared, there's cosine squared, and blah. Okay, we've got the integral set up, right? That's the part that's most important. So here it is on the computer. Is that the right integral? Yeah, that's what we had, right? So ignore all this. I mean, actually, when I typed these notes up many years ago, there wasn't Symbolab and Wolfram Alpha. Didn't exist. So couldn't just go to a computer and type these in, or just put these integrals in. Now you can. So pretty sure you'd be able to get 65 pi over 4 now. But I'm not going to go through any of that. Y'all can see here that when you do the first integration, here's what you have to integrate. And then you integrate that with respect to r, and you get this integral, and then you wind up with like cosine squared, sine, cosine. So you do some trig stuff from Cal 2, trig integrals, power reducing, half angle. On your test, on your final exam, I don't think, I need to go and look at it, but I don't think you're going to be calculating anything like this all the way through. It just take up way too much time. So it'd be more about like setting up. But, okay, can we go to the next example? Hey, I have a quick question for you. So you remember when we were doing double integrals? It has nothing to do with this problem, just thinking. Remember when we were doing double integrals? And we were talking about this region on the ground, R or D or whatever we called it. What was the first type we had? The most basic one. Well, it's constants, right? And it was a rectangle, right? A, B, C, D, right? And it gave us that rectangle. That's what a rectangle looks like in Cartesian, right? And then I said, okay, well, what about if we go polar? So this is Cartesian. This is a rectangle here, right? Double integral, our region R is a rectangle. It looks like here. What does a polar rectangle look like? Remember, it was like our angles between two constants, and our radius was between two constants. So it looks like that. Right? That's a polar rectangle. Theta's between two constants, and then radius, yeah? Okay. Now we move to triple integrals. And the solid E, right? What was the most basic Cartesian box we could have? Yeah, like a cube. Although the dimensions don't all have to be the same, right? Like this is restrictions on A and B this way, right? Here to here would be like C and D. And then I think we used R and S for these. But your X's are between two constants, Y's between two constants, Z's between two constants. Yep? That's Cartesian. Okay, now triple integral over E. But now we do polar slash, not polar, but cylindrical, right? What does a rectangle or a box look like here? This is a box, right? What does a box look like here? Like that, but what? Extruded, yeah. I like that. I was going to say you must be solid, you use SolidWorks or something like that. Yeah? Long time ago, okay, yeah, it's an extrusion of that plane, exactly. So, anybody here use Fusion 360? No? I was looking for some help with it the other day. Okay, so it's that, but extruded which way? Just up and down, right? Because Z is between two constants, so it would look like, I don't know, it's going to be kind of hard to draw, but not the worst thing I've drawn. Yeah, not bad, right? It's just that extruded. So your theta is between two constants, right? Your radius is between two constants, and your Z is between two constants. Okay, sorry, I'm gonna come back to this in a minute. When we go to our third coordinate system, we're going to talk about what that looks like, because it's not like any of, like, it looks very different than these. All right, so find the volume of the solid between the cylinders. Okay, kind of similar to the previous problem, right? Between these two cylinders that both go up and down, one has a radius of 2, the other one has a radius of 4. But it's also, the solid also lies inside the sphere. X squared plus y squared plus z squared equals 36, which is a sphere of what radius? 6. You don't see it? Kind of hard to imagine. Well, so it's like the pool noodle. I can't say it. Pool noodle, right? It's the pool noodle, but we cut it with the sphere on top and we cut it with the sphere on the bottom, right? I don't know why I don't have the whole thing shown here. I just have the end result. There's the end result. There's your two cylinders, the space between them, and then the sphere comes across the top and shaves off a curved top part, and then a curved bottom. It's important that that top is curved, right? Okay. So what we want to do here, find the volume of it. Find the volume. Ooh, we want the volume of that. Okay, how do we do a volume? Triple integral of 1, right? So I want to do the triple integral over that solid E of 1 dV, right? That'll give me the volume of it. So, shadow on the ground. There's not really a shadow on the ground because it goes all the way through, right? What do y'all say we use some symmetry here? What do you say we just do the top half? Yeah? And then when you cut it with the z equals 0, then it's easy to see the shadow is polar region, right? Yes?
Why is it 1 dB?
So remember, this is one of the big, I actually ended class with this last time, well, before I started throwing shit around the room, that when you have triple integral of 1, that gives you the volume of that solid. If you have double integral of 1, it gives you the area of the region you're integrating over. Remember that, the 3?
Yeah,
okay. So, all right, so I'm going to do this triple. Tell me about the ground here. Yeah, so polar though, right? That's great for polar. Theta's between, R's between, Z's between. So we're in cylindrical coordinates here. All right, let's go around the room. We'll have fun today. This table first. Theta? 2. 0 to where? Your angle. 2 pi, okay. All right, we're going to keep going. R? Two, 4. Good, everyone? Back. Z? What are you thinking for Z? Well, what are you thinking? I mean, is there, remember, we're only going to do the top half and double the answer, right? Right, we agreed to do that. So if we're going to just do the top half, what would our bottom be then?
0.
Yes.
Oh, yeah.
0, the ground? Okay, since you got that, you get the top now. So what would the top be? What are your thoughts? I mean, what is the top surface? Hold on.
I was going to say, is it something with 36?
Well, I don't know. That's what I'm asking.
36 or 34?
What is controlling the top of this thing? What does the top of this thing look like? Is it flat? Well, my drawing sucks. Was it a flat top? No, it's curved. What's controlling the curve? Okay, I think I'm making my point. Whatever's in there is not what's up here, okay? So I'm not sure what you're doing on that, but are we good? Okay, so anyone, what's controlling the top? The sphere. Solve it for z. There you go. And that'll be the top. So solve it for z, and what do you get? Square, well, wait a minute, hold on. Okay, let's do it. This order doesn't matter how we do it. Square root of, is it plus or minus, or? It's just the top, so we're going to just do the plus, right? And then 36 minus r squared. R squared. Why? Because we know we're going to polar, right? Cylindrical. What's x squared plus y squared? R squared. And then we bring that to the other side. So there we go. That's it. That's it. Any questions? Are you all understand? So we just set this up. Integral, okay, 0 to pi, 2 to 4. And then, yeah, 0 to the square root of 36 minus r squared. And then what are we integrating? What's our integrand? 1 d, oh, r. Almost forgot it. Almost forgot it. Almost forgot it. Because we're switching, right? We're going out of Cartesian. We're going into cylindrical / polar. Now you can say d, z, d, r, d, theta. Can we switch the order of r and theta? Can we switch that if we switch these? Yes, because they're constants. But we can't put this one in the back, right? All right, that's it. Oh, wait, hold on. 2. Right, because it was only the top half. That should be it. That should be the volume. Now, I mean, I want us to somehow appreciate this a little bit, right? If we were to walk into class today and I were to ask us to find the volume of that, do you even think that, well, go back to the beginning of class, right? Like when you walked into Cal 3. If I said, hey, find the volume of that. Can you imagine the type of geometry you'd be trying to do to figure this shape out, right? It'd be pretty complicated. I mean, I think we're in business. Now we just go to a computer and do it, right? And the volume is approximately, did I double? Hold on, let me make sure I doubled the answer here. I don't want you to give you the wrong. Oh, I did mine different. I included the bottom. I said instead of going from 0 to the top, I went from negative of that to the top. Right, you see it? And we're going to get the same answer. So I didn't double. 383.595. All right, cool, huh? That's it. There's your homework assignment. 3 problems, yes.
We're going to do one on the test where we have to actually solve it manually.
I will not, to me, that's a waste of time.
Okay.
You know, like you took Cal 2, so you should know how to integrate in theory, right? I'm more concerned about can you set up a couple of these problems, right? Because that's the part that you can't go to a computer for. Not yet, I guess. Not yet. All right, you ready for the next and last coordinate system? Cylindrical is not so bad, right? Not so bad. It's just polar in 3D. That's it, right? So now we go to our last one. And this is the one that really trips people up. But it's the most practical one. It's called spherical coordinates. Okay, now, before we get all bogged down with how to convert from Cartesian to spherical, because it looks absolutely horrific, I want us to talk about just how the system works first, all right? So let me get my 3-dimensional space here. Spherical's important, right? Mostly, right? Because we live on a frickin' sphere. Roughly, a sphere. Right? All right. Here we are. X, Y, Z. All right. Let's say we have a point in space. Let's let it be the, I don't want to look at the projector. So let's let it be that sprinkler head over there in the corner. See that sprinkler head over there? Okay. Cartesian. Cartesian. X, you go Y, up Z, right? Cartesian. X, Y, Z, you're at the point. Cylindrical. How do I get there in cylindrical? Angle. Right? What? Radius takes me where? Right below it, right? And then Z takes me up to it, right? See the difference between those two systems? X, Y, Z versus theta, R, Z. Okay. Here's the way spherical works. We start here pointing out the x-axis, and we start by looking straight up like this. We're just standing here like this, okay? Looking straight up. And now you're going to provide me three things. First, you're going to provide me what's called phi, or phi. And that's the angle that's going to take you like this and start opening you down towards the x-axis. And what you want to imagine is that angle is eventually going to point you at that, okay? So I give you phi, then theta. Theta is this way, kind of like theta was on the ground, but now we've got this phi action first. Phi, phi, theta, and then rho. We call it rho. It's R. How far to walk out. See the difference? Two angles in one distance. So Cartesian is just like distance x, distance y, distance z. Cylindrical is theta, radius, distance, and then how far to go up. Spherical is phi, theta, rho. Now, what does a spherical rectangle look like? So if I tell you, oh, and here's phi. Phi is between two constants. I'm just going to put number here, number. I could use alpha, beta. Theta is between two numbers, and then rho is between two numbers. Can you visualize that